Well, good morning in the meantime. Okay. So this presentation now, I already announced it yesterday or the day before, I don't remember. This is now not an Intel presentation, okay? It is on an Intel slide deck, just to remind you, that this is an Intel workshop. But this is actually more a presentation of the OpenMP language committee than it is an Intel presentation, okay? And that's why the disclaimer is a bit different. So instead of, lots of legal tests, it just says, it's not an Intel presentation. The stuff that I'm going to show in the next couple of minutes is in flux. So this is what the OpenMP language committee is working on right now. So anything you will see will change, okay? But the concepts will roughly stay the same. And the idea here is that during the lunch break, during the coffee breaks, I want to kind of solicit feedback from you guys as you work on applications, if that is going to be useful for you, or if you say, yeah, it's a nice feature, but I'm not going to use it anyway, so you can as well leave it out of the language, basically. Okay, so everything I'm going to tell you is to be taken with a grain of salt, actually with a lot of salt, and it will likely materialize in 2018 with OpenMP 5. And what I'm going to talk about is the memory API. So we had, I think yesterday, we had some conversation about fastmem attributes, or the day before, about fastmem attributes and how to modify allocations in C, C++, and Fortran to go into high bandwidth memory. And some people actually said something like, hey, you call this fastmem, what's fast? Right? And so this is what this presentation is about, basically. Okay, so if you look at hardware right now, there are different flavors and different kinds of memory, right? So there's something like high bandwidth memory, MCD-RAM or HPM as a trademark name. There are scratchpad memories. There is NUMA, so there's slow memory and fast memory compared to the local core you're running on. In the future, there might be something like 3D crosspoint, so non-volatile memory that is not exposed as a disk, like a block device, but more like a byte addressable memory space that has different properties than the traditional DRAM, okay? And then whatever you look at right now, how storage works, there are different page sizes. So when you do module avail on a Cray system, you will see that the system roughly supports like on the order of 20 different page sizes, okay? Then there is alignment. So there's native data type alignment, like 8-byte alignment for double, 4-byte alignment for integers. There is SSE alignment 16 bytes. There is AVX alignment 32 bytes. There's AVX 512 alignment 64 bytes. There is page alignment, depending on what page size you used. You may want to align to the page sizes as well, right? So there's different alignment today already. There's the NUMA distance. So, it's in a 2-socket system, you've got two different kinds of distances to the memory. In a 4-socket system, it becomes even worse. And then there's something like Knight's Landing, where when you configure the system to be in sub-NUMA cluster mode, you end up with 8 NUMA domains. Okay, so it's really complex. There might be multiple devices. So, you guys have a big GPU cluster, and how great wouldn't it be, how great it would be if you would be able to say something like, allocate memory on my coprocessor device, in this case a GPU, without actually using something like CUDA Malloc, but instead use something portable so that when you move to the next machine that has a quantum mechanical accelerator, you could allocate memory without changing the language in your application to be on that new coprocessor device. Okay, and then there are things like thread safety. So if you want to allocate something that is shared between all your threads, or that's potentially private. Right, and I didn't speak about GPU, local scratchpad, read-only caches, and all that kind of stuff. So there's a lot of different memory around in the system, and it's really hard to program that. Now the fun thing is, the plain old Malloc, it's one of the deficiencies in C, or the new allocator in C++, or plain old Fortran allocate statements, they are barely good enough to do that, right? So you can say Malloc, and then something happens, right? You don't even know if Malloc actually allocates a physical page, or if it does first touch policy. Right? It's completely agnostic. You can't tell. All you get is like a contract, a promise that you will have an address that doesn't cause a seg fault. Right? But that's almost all guarantees that you will get from a malloc. And the same is true for news, for new and allocate. And then there are special functions like intrinsics. The intrinsics header brings you something malloc that has an alignment property at least. You can inject a memory allocator by LD preloading it. There is TC malloc, JE malloc. There are tons of threaded allocators that you can inject that way. There is NUMA-CTL. There is POSIX, MEM, whatever. There are system calls to move memory around to do page migration. And depending on where you are, there's some obscure environment variable that you can set to modify things in your system, right? But none of them is actually portable or gives you enough flexibility and expressiveness that they can actually control the memory allocation the way you want it. Okay? Yes. Right. So one thing we try to do is with memkind, we kind of at least started something, right? And to be honest, memkind is not good enough. It works okay. It is okay for some of the simple cases like MCDRAM allocation, but it doesn't tame this problem, right? It's way more complicated. And this is an attempt to at least standardize it in a way. I'm not saying that it's the optimal solution, but that's the feedback I'm trying to get from you as well, how you find that. Okay? So what we want. We need something that is extensible, right? So we want to have, first of all, a standard programming model, right? But we want to have an extensible programming model so that when, I don't know, a year after OpenMP 5.0 comes out, a new, completely unforeseen memory kind develops, that we don't have to change OpenMP again, right? It somehow needs to be extensible so that it can formulate new properties in this thing. The other thing, and that's sometimes completely forgotten by developers, it needs to be composable. Who of you tried calling MKL, multi-threaded MKL, from a threaded context already? Come on. Did you ever try that? It's fun and happiness for everyone, right? It just falls apart because MKL, OpenMP itself, in this regard, is not composable. And then when you call MKL from a threaded context, basically, I'm tempted to say hell breaks rules, and we want to avoid that, right? So if you have a library that works on memory, that potentially allocates memory, like your favorite STL container, you want to somehow be able to interject into that library, in this container, that it should draw memory from there, right? Without changing the container. Okay? Of course, it needs to interact with OpenMP mechanisms. We need to be able to retarget to new memories. So it needs to be flexible enough that when you move from bistained to another machine, that you don't have to rewrite all your allocation in your application, right? Only gradual improvements you need to make. And then there's all kinds of different data. So there's static data that is somewhere in the data segment of your application. There is heap allocated data and there's stack allocated data. And sometimes you want to express that a variable that is on the stack should actually go into high bandwidth memory because it's an array that you want to access from the high bandwidth memory. Okay? So you need to be able to control all that. And this is what TR5 does. So TR is short for technical report. That's the way that we invented like a couple of years ago in the OpenMP language committee to actually go out to the public and say, these are the crazy ideas that we're thinking about. Right? It's not a specification. It's not yet formalized. But here's what we're working on. This is what might end up in the final specification of OpenMP some version. Please comment on it. It's kind of a sign of life so that we don't, vanish for 3 years and then all of a sudden pop up at supercomputing and say, hey, here's the new OpenMP. Right? So a little more interactive than we used to be before. Okay? It's not yet complete. It's just the basics. And I will list you all the aspects that we're working on, and you will see that it's a bloody mess to get that right. Okay? Okay, and the idea is also, since it's OpenMP, that Cray is behind it, Intel is behind it, NVIDIA is behind it, so that everybody who sells major HPC systems actually supports that, and so that there's a certain chance that you can get something portable. Okay, so this is the easy example. Instead of Malloc, you just write OpenMP Alec. You're done, right? And this is something where I think that OpenMP is a nice programming model. We had yesterday, I think we had a conversation over a beer, whether or not, if it's an evolutionary programming model or revolutionary. Revolutionary means MPI, for instance, right? It's all or nothing. You can't have an incremental MPI code. That doesn't really work, right? You have to really move everything to MPI, otherwise it doesn't run. Right? OpenMP is more incremental. So you can start, with a, I don't care about anything, pragma saying pragma parallel 4. Right? And then the compiler does something for you. And then you can build on top of that and, build a more fine-grained parallelized program or more performance into your program. And we try to do the same here. So all you need to do is to get a first start is OMP Alec. Basically like you would do in a regular C program. And then this OpenMP Alec is smart enough to ask an environment variable what this allocation actually means. So what is the allocator that is used to do those allocations? Right? And if it's something simple like a KNL where you just want to say put everything into MCDRAM, you're already there. Right? You just need to set an environment variable, say allocate from this special memory, and you're done. Okay, if that is not sufficient, you can go the hard way. And bear with me, it's a lot of text that you have to write, but that's not our fault. That's shitty C language, because C is not expressible enough so that you need to write, a lot of function calls on opaque data types so that you can fill in things without exposing too many implementation details. That's why the interface is so completely messed up. Right? If we were to use something like Python or C++, this would look a lot simpler, but we have those 3 base languages, C and Fortran, and C and Fortran are horrible when it comes to opaque data types or transparent encapsulated data types. And I'm going to explain that in a minute, what all that means. So it's just, that there is an easy way and a more complex way that gives you detailed information about every aspect of your memory allocation. Okay? Okay, so what do we have in TR5 already? So what we have is we have memory spaces, we have allocators, we have the allocate directive, we have an API to talk about all those concepts in language, in code, and we have an allocate clause. And I'm going to show you all that in a minute. Okay? Okay, so memory spaces. So there are 2 different things in memory, that orthogonal things that you need to consider. First of all, there are traits. Like, what is the memory? Is it read-only? Is it read-write? Is it volatile? Is it non-volatile? Is it slow? Is it fast? And then, slow being decomposed into low latency, high bandwidth, or, whatever, right? So that, there's just properties of memory. And you need to, some way to describe the memory that you want from the system. Right? So you don't want to say, I want to allocate from this physical pool, but instead what you want is, you want to say something like, I want high bandwidth memory, and then have the system give you whatever it thinks is high bandwidth memory. On a KNL, that's potentially MCDRAM. On a NUMA domain, this could be the local NUMA node that you get memory from, and the remote node would be the slow memory. Right? If you don't have high bandwidth memory at all, high bandwidth memory might actually mean the standard memory. Right? So that's why we have those traits. Okay? Some of them are descriptive. where you just express a high-level wish of what the property of the memory should be, and then the memory system or the implementation fills the gaps, right, and supplies whatever it has. And then others are prescriptive, like alignment, where if you say I want 64-byte aligned, then the runtime system doesn't change it, right? It will adhere to what you're asking for. Okay, and then we have some OMP default mem traits. And that's kind of the properties of whatever is considered the default memory space in your machine. So for instance, on a Xeon, this could be the plain old DRAM memory. On a KNL, this could also be DRAM. On a future architecture that doesn't have DRAM anymore, this could be the MCDRAM or high bandwidth memory that is already on the processor. So whatever the machine or the implementation, the framework, the ecosystem considers as the default memory where you should draw your default allocations from. Okay? And then we have some available memory traits. So we can talk about location, so where it is with respect to core, socket, and device. The distance, I'm here, then there's far memory that is far apart, and then there's near memory that is local. Then it could be optimized for latency, bandwidth, capacity, or non-optimized memory. You can ask for bandwidth, at least highest and lowest. And yeah, I can see a couple of funny looks in your faces. It's like, yeah, but what if I have, ultra fast memory, not so fast memory, not so fast memory, and then slow memory? How do I express that? Well, it's not complete yet, right? It's horrible, right? There's too much flexibility in how hardware is built today, so that you can't cover all the aspects, right? At some point, you need to draw a line and say, this far and anything else beyond that line is out of scope. Okay, then you can ask for latency, like highest and lowest. You can ask for capacity, for available memory, for the permissions that you have on the memory. So you can also ask for read-only memory if you want it. And then the page size, right? So that you could also do performance optimizations. And then there are matching rules. So for some, an equals basically means it's prescriptive. Right? If you want, say, read-write memory, the system shouldn't give you read-only memory, right? Then the allocation just needs to fail because your program will fail. If you're asking for capacity, right, that's rather descriptive as long as your request is fulfilled with memory that is at least as large as you're asking for. Right? If you ask for 10 megabytes, the system shouldn't return you a pointer that only is capable of storing 5. Right? And then there are some, like this little snake line, where it says, try to be close. Right? So if you ask for far apart memory, then the system tries to pick something that is close to what you're asking for. Okay? So that's basically the memory traits that we're talking about right now. And these are the allocators. So basically what you do is you construct a description of the memory that you want by composing those traits. So for instance, what you would do is you would say, I want memory that has a page size of 2 megabytes, that I can read-write, that has at least available capacity of 200 megabytes. So I want 200 megabytes. I want high bandwidth with lowest possible latency. Right? So these 5 traits you compose, and then you construct a memory space object that describes that, and then you build an allocator around that. And then the allocator will take this description, find the memory in the system, and when it does an allocation, pick memory from there and give you back a pointer so that you can access that memory. Right? Okay. You can ask for several things, like you can ask for the alignment again, you can ask for the thread model, whether or not you want pin memory, so if you want allow the system to swap it in and swap it out, depending on what you want to do with it. Then you can ask for a fallback. That's also very important. Right? The default behavior of NUMA systems is to spill over into the next available NUMA bucket or NUMA domain. Right? But if you have a code that is really bandwidth sensitive, and the system doesn't offer you enough MCD-RAM or high bandwidth memory, you may actually want to know that. You want to get a hard failure from the system saying, I don't have enough, like 32 gigabytes of high bandwidth memory available for you. I cannot satisfy this allocation request. Right? And then you can either terminate, because then it makes no sense to run it all, or what you can do is you can fall back to slow memory and change your algorithm. Or whatever you want to do, right? Or do some out-of-core computation with whatever is the memory capacity. There's a question? Okay.
So how does OpenMP knows it? Which memory is which? Is there a configuration file, or is it at runtime?
That's implementation defined. So somehow the implementation needs to supply the knowledge how to fulfill those allocations. That can be a dynamic configuration file, that can be hard-coded in the library, that can be supplied by a library that is injected from the queuing system. We don't talk about that. This is, on the programming language level, right? As well, like it's similar to what C does, right? If you write a for loop in C, C doesn't tell you how the for loop is mapped to the machine, right? It's basically free an implementation choice. But we have some vendors that are already thinking about having a configuration file where you can inject the mapping between the memory traits and the properties of the memory and the underlying hardware.
Because on KNL it can be very dynamic. It can be very dynamic.
Yes, yes. For a KNL system, it's rather easy, right? You got high bandwidth and slow bandwidth, right? And then potentially NUMA domains, right? But the NUMA domains are things that you can find from the system and hard code in a sense that you can ask the system. But yes, there are more elaborate ways. If you think about a storage cluster, right, that has some high capacity memory modules in a storage rack, then things are of course a lot more complicated than just saying I want that. So there need to be mechanisms to map that to the underlying hardware. Okay, so there's an API to do all that. I already said that. So there's allocation. There are functions to talk about memory spaces and to add features or traits to that memory space, and then hand it over to an allocator to actually allocate from that memory space you just described. Okay? What we can do is we can do a regular Malloc type call that just returns a pointer. We have an allocate directive. That is now more for the Fortran programmers that need to modify the allocate statement. And then we have allocate clauses so that on the pragma level you can decide is that an array or a private variable should go into a different memory space than the normal or the default. Okay? So which one should you be using? So if you're talking about heap data in CC++, you can of course use the API. In Fortran, yeah, with ISO-C binding you can do that, but you don't get a real Fortran pointer out of that. You can use the directives in Fortran to modify the allocate statement. For static data we have directive. In C we didn't yet talk about that a lot. It's because where the data segment is allocated is actually a link time decision in most systems. So it could be harder than expected to modify that. For automatic data, you can use a directive. And then there's OpenMP data, so shared, private, first private, reduction variables, and so forth. You can use the clause to modify these. Okay, allocation. And I'm now going to give you basically an example that I'm building up. Okay, so the default, that's kind of what I was showing on my second slide or so, is an OMP Alec that just doesn't care about anything. Right? Then we just retrieve the default allocator, and the default allocator can be controlled by an environment variable. Okay, that's kind of the easy case, and also probably sufficient for most systems where you just want to talk about high bandwidth memory versus low memory, for instance. Then the other thing that you can do is you can make the example slightly more complicated by creating an allocator, feeding that into your allocation function, right? And then the allocator takes a memory space that it should draw memory from. And this is now how things become composable, right? If you think about a library that does memory allocations, the library, of course, needs to be changed, right? It needs to use those new interfaces. But now you can pass the allocator into your library as a parameter, as a trait, or whatever, right? If you think about C++ STL, what you can do is you can specialize a container template, not only with the data type it should use, but you can also pass an allocator object to it. Same idea, just more generic because we have to support C, right? So the allocator basically is a pointer, and you can pass that pointer around into a library, and then when it does an OpenMP Alec, it can use that passed allocator to work on. Okay, so now we initialize an allocator, and it needs a memory space, right? And the memory space is the default, whatever the system offers as memory traits. Okay, now let's make it more complicated. So what we can also say is, well, from the default memory space, please allocate such that the thread model is exclusive. So that means that each thread that performs an OpenMP allocation gets a private allocation from that memory space. Okay? Then we can make it more complicated, and now I'm kind of building the more complex examples now stepwise. The other thing that you can say is, well, I don't want the default memory space, I want a special memory space. I want to say, I want maximum bandwidth with whatever highest latency, I don't know, and I want page size to be 2 megabytes. And that's the description of my memory space. I'm looking in the system for such a memory space. I'm adding my allocation traits for thread private storage, and then do an OpenMP Alec from one of my OpenMP threads. And what I'm getting is thread exclusive high bandwidth memory with a page size of 2 megabytes. That's the idea. And that was my previous example, basically. Okay. Here's an example how you can use the allocate clause. So you can allocate, you can define some struct, you can allocate it with an OpenMP pragma, and then you can say, use this special allocator that I was defining on the previous slides to store that or to retrieve memory for this struct. Okay, and you can also do, like, you know, here's an example of how you can do a global allocation as well. If you're happy with Fortran, it basically looks the same. So you can either say, you know, allocate A in these traits with an alignment of 64. Now we are, you know, not using an allocator object, but instead we're using the alloc traits in clauses directly. Or you can modify an allocate statement to also use a different allocator to get the memory for that allocation. B.
So you allocate down below, but you haven't described any traits for B, only A.
Well, here I'm using an allocator, right? So somewhere there needs to be an initialization of that allocator, as I was showing in the C examples before, right? And then the system knows where to put B, basically.
What does that look like? Is that
it's
directives, or?
Yeah, it's basically.
In Fortran, it's going to look like this.
It's going to look like this. Yes, yes, and that's why you know I was saying that C Fortran have crippled interfaces in the sense that it's really hard to have a Fortran 77 or Fortran 90 syntax that describes an opaque data type, right? If you would use Fortran 2008, things would be different. But since OpenMP is still, I think, based on Fortran 90 or even supports Fortran 77, we need to go with a very fine-grained, very verbose interface. But the good thing is, you know, usually what we thought is you don't have to write that anytime you do an OpenMP Alec or use an allocate. You can have a Fortran module, like one source file that defines all your allocators. You don't need 10,000 of them. You just need to describe, you know, for some certain data structures you care about, what should be the allocation properties, and you can encapsulate that in, you know, a single Fortran file, and then it basically boils down to importing this guy here from some other Fortran module, and it will do the right thing. There's a question.
Yeah, so go back to the C++ example there. So by putting the allocation into the pragma, is there now a fallback when we do not compile with OpenMP?
You can still, yes, you can still, well, it's still, so in this example, if you ignore OpenMP, it will do a default automatic allocation, whatever C++ or C requires. It's just a stack allocation. It's just that when the compiler understands OpenMP, that the compiler now knows that B should be allocated somewhere else. It's still correct regular C, C++ code. Right? With one backdoor, of course, if you use OpenMP _ Alloc, right, and you turn off OpenMP, then OpenMP Alec is gone from the syntax, and then you need to switch back to regular Malloc. So you probably need to encapsulate that in some wrapper so that you can switch it on or off depending on the compiler options you use. Right? Okay. I'm almost through. So that's the allocate clause. I was talking about that. Then the basic thing that you can do is you can for instance, for this private variable up here and the reduction variable, you can say, I want to allocate P and R with these allocation traits, so they should be 64-byte aligned, and the memory traits should be allocation near, so they should be on the local NUMA domain. Okay? So you don't necessarily have to construct all the glory of an allocator. You can also use, if you want to keep things simple, you can also use those traits and memory traits and memory spaces directly in those clauses. Right? Again, of course, then if you switch to another system, you might need to change those. Right? But we give you the option to be simple or very, very fine-grained with very, very fine-grained control. Okay. So what I was showing here is about 15% of what we need to do. Okay? Because this is everything we need to talk about. In green, you see roughly what TR5 already contains. We are not talking yet. We started the conversation, but we didn't publish it yet. There is remote device allocation, right? Especially with NVLink in GPUs from NVIDIA, what you can do is they have now this virtual shared memory across graphics cards and the host CPU, so the host memory. And then you want to have some mechanism to allocate data into the GPU directly, right? We don't cover that yet. We don't cover NUMA yet. So we cannot express how to allocate data in a NUMA system. We can only express certain memory traits, but not in a NUMA system. If you recall my stream benchmark yesterday, the numbers, what you need to express for the seventh topic on this list, what you need to specify is scatter the memory, because I'm scattering my threads that will be working on this memory. Right? So there, for NUMA allocations, you actually need to know how you're going to use the data. And that's even more complicated to express. Right? Resource querying, that basically relates to what you were saying. Right? How do I find out if I should be asking for non-volatile memory? Should I have an API that delivers me all the memory traits in the system? And how do you enumerate all those? Then there is, for instance, the gen graphics parts in our processors, they have special instructions. So if you want to read data from a special scratchpad memory, you need to use different load instructions. So this now influences the code generation, which in turn means that you cannot simply pass an allocator with different memory traits, like allocate from a scratchpad memory into a kernel, because you need to compile the kernel differently in this case. Right? So that's another problem. C, C++, and Fortran specifics, right? New, delete, object orientation in Fortran, all those nasty things. Additional traits, nested memory spaces. Beautiful topic, right? You can think about something, a high bandwidth memory that has a scratchpad area. That's even different, right? You want to probably do named allocators, static allocators. You know, there's a lot of additional topics where you need to talk about. But I think the first column, that's the most important part of the whole topic. And as you can see, we only covered 5 of them already, and it's already a pretty big topic for us. All right, so I want to hear your feedback about it. Not necessarily now. We can take it offline in the coffee break. You can shoot me an email. You can post on our forum. So the TR5 is open to public. You can go to openmp.org. There's a forum where it says something like technical report 5 feedback, and then you can, you know, flame against TR5 in this forum. We're going to read it and take your feedback if it's not too nasty. Okay, that's pretty much it. That was the OpenMP part of this workshop. Thank you.